Welcome back, everyone. In this video, we're going to be asking ourselves the question, what happens to pH over the course of a titration, specifically an acid-base titration? Does it just go up linearly or go down linearly? And why is it that getting to the end point in an acid-base titration is so finicky? You know, you can be strolling along, just adding droplet by droplet, and then all of a sudden you get close to that endpoint and you think you've got it, and then you add one more drop and then you've gone too far. Why does it get really, really sensitive when you're close to the end point? And we're gonna go over why that is mathematically here. Some of it will be a review of how we calculate pH from concentration of hydronium ions and hydroxide ions. And then there will be some stoichiometry mixed in with it too. All right, so here we've got just a scenario here where we have a 25 milliliter sample of 0.10 mole per liter hydrochloric acid. It's being titrated with a solution of 0.10 mole per liter sodium hydroxide. So starting off with an acidic solution inside the Erlenmeyer flask, and then we're going to start adding drops of sodium hydroxide to it. And what we're going to do is we're going to look at 4 different situations, 4 different timestamps over the course of the titration, A, B, C, and D. The first one is before we add any sort of sodium hydroxide. Then we're going to calculate the pH after we add about 24 mils of sodium hydroxide. Then we're going to calculate the pH after we've added exactly 25 mils, so the same volume that we have of the acid. And then we're going to look at what happens to the pH when we're just another milliliter after that. And then we're going to plot it all on this particular graph here. All right, so I've written the balanced chemical equation already. Just going to talk about the graph. On the graph, on the vertical axis, we have the pH. The pH is dependent on the volume of sodium hydroxide we add. And that is labeled here on the bottom on the horizontal axis, and we're recording the milliliters of base that we add. So let's dive in and calculate the pH before we add any sodium hydroxide. So let's look at situation A. So before any sodium hydroxide is added, what we have is a 0.10 molar solution of hydrochloric acid. So we could say, and because hydrochloric acid is a strong acid, we can, because it ionizes 100%, we could just say the hydronium concentration is the same thing as the concentration of the acid. So its concentration is 0.10 moles per liter. So that means its pH is the negative log of 0.10. So the pH there, remember we take the negative logarithm of the concentration, and I get a pH of 1. So in situation A, before we add any sort of sodium hydroxide, so when the volume is 0, the pH is going to be 1. So it's an acidic pH. Makes sense, because we're adding base to the acid. All right, so let's look at situation B. Situation B, I've added 24 mils of sodium hydroxide. All right, so 24 mils of sodium hydroxide is going to neutralize a certain amount of hydrochloric acid. So let's go determine that. Well, I know I have of the hydrochloric acid, I've got 25 mils, which I'm going to write out as liters. And it has a concentration of 0.10 mole per liter. And for the base, sodium hydroxide, I added 0.0240 liters, or 24.0 milliliters, and it has a concentration of 0.10 moles per liter. So with both of these volumes and concentrations, I can determine the number of moles of each. So my number of moles of acid is going to be 0.0250 times 0.10, and I get 0.0025 moles. I can do the same thing with the base, sodium hydroxide, and you'll get 0.0024 moles. All right, so now what we can look at these two numbers and say, well, which of them am I going to have some leftovers of? Well, it's a 1-to-1 ratio, and it looks like I don't have enough base to neutralize all the acid. So how much acid is remaining? So the number of moles of hydrochloric acid remaining is going to be 0.0025 moles, subtract 0.0024 moles, and that gives us an answer of 0.0001 moles. Okay, so I've got a little bit of acid left over, and now I want to figure out its pH. Well, at this situation, at this time, the volume is not just 25 mils anymore. Okay, the volume is 25 mils plus the 24 mils from the base. So that means my volume is going to be 0.00. Nope, that's not right. Not 00. Let's see, 0.0250 liters and 0.0240 liters. So that means it's going to be 0.0490 liters. So I have my number of moles of acid. I have its volume. I can determine its concentration. Concentration will be 0.0001 moles divided by 0.0490 liters. So that gives me a concentration by 0.0490 of that. So 0.002. Okay, and to determine its pH, I'm going to take the negative log of that number because it's the hydronium concentration. And I get an answer of 2.69. Yikes. So this is kind of the weird thing about doing acid-base titrations with strong acid and strong base. Okay, at 0 milliliters of base added, I had a pH of 1. After 24 mils of base added, so like I'm way up here, I've like hardly made a dent. Like I'm at 2.69, so that's like not even halfway between. So all I've really done is I've gone from here to here. So there's been hardly any sort of change in the pH. All right, let's see what happens after I get to where I think I'm going to get like to neutralization here. What happens here? Well, at situation C, I've added 25 mils of sodium hydroxide. So I'm not going to write out all this stuff again, okay, but we can kind of do the math here, think through it. Number of moles of hydrochloric acid remaining, well, it's going to be 0.0025 moles minus 0.0025 moles of the base. So because it's a 1-to-1 ratio, I've completely neutralized the acid. And there should be 0 moles of base also. So what is really present? What's present here in this solution at this time? Well, I've completely neutralized the acid. I've completely neutralized the base. So these two things just cease to exist. They're not there anymore. And what I have left is sodium chloride and water. And it's going to be predominantly water because this reaction takes place in water. So really what I'm trying to figure out here is what's the pH of water? Well, we know that the pH of water is 7. Okay, pH of water is 7, so that means once I've neutralized all the acid, a neutral solution should have a pH of 7. So here's the cool thing. At 24 mils of base added, I had a pH of 2.69. I add 1 more milliliter, and my pH jumps up to 7. So it's almost a near vertical increase. And let's just look at the last situation now. After I add 26 mils of base, so I add 1 more milliliter, what happens to the pH? So I'm just going to record it right here. So without doing the whole calculation over here again, let's just figure out how much base we should have left over. So we added 26 mils of base, so we should have 1 more milliliter of base left over. So let's figure out number of moles of sodium hydroxide remaining. And I should have 0.0026 moles, subtract from 0.0025 moles of the acid. So that tells me that I have 0.0001 moles of sodium hydroxide left over. And the volume, remember to add the two volumes. I've added 26 mils of base and 25 mils of the acid. So that's 51.01 mils, or it's 0.0510 liters. So what is the concentration? The concentration will be 0.0001 moles over 0.0510 liters. And remember, this is concentration of the sodium hydroxide. Get that number right, I think I did. So I get a concentration of 0.00196 blah 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 moles per liter. Now, what is that concentration of? Well, remember, that's the concentration of hydroxide ions. So when we take its pH, well, we can't take its pH directly. When we do the negative logarithm of that number, which I should have recorded, let's just do this again. If I take the negative logarithm of this number, it's actually giving me the POH. And the POH is 2.70. So to find the pH, I have to subtract the POH from, oops, let's do 14 minus that number. To find the pH, we do 14 minus the POH, and we get a pH of 11.29. So this is pretty crazy. At 26 mils, we're up to roughly 11.29 of a pH. And as we keep adding more and more base, what we'd notice if you kept going with this calculation to figure out how much you'd have left over, the pH curve would start to look something like this. Okay, so this is kind of the weird thing with titration. This is one of the reasons why you can go from like yellow to blue very, very quickly, like within the span of a few droplets. So all through this range, your pH indicator should be yellow. Okay, and then until you start getting close to the 7 range, so once you get close to the end point, so the end point is when the pH changes color, it's green for a little bit, but then if you add like a couple drops, maybe even less, okay, it'll start to go blue. And it'll stay blue because it's now a basic solution. So there's a few things to kind of keep in mind here. For these types of titrations, strong acid, strong base, pH equals 7. And we say the pH is equal to 7 at the equivalence point. The equivalence point is when the acid and base have neutralized each other. So the equivalence point is where we get neutralization of the acid by the base, or vice versa. Okay? So pH is 7 here at the equivalence point, and when we do titrations, we try to pick an indicator, a pH indicator, that is going to change color close to this equivalence point. We don't want to pick a pH indicator that's going to change color way down here. You know, if we had a indicator that went from yellow to blue, you know, between 2.3 and 5, well, it would have changed color way before we would have gotten to that stoichiometric equivalence. We want to pick an indicator that is changing color over this vertical area of the pH curve. So bromothymol blue is a really, really good indicator to use here because its pH range is on this vertical section of the pH curve. Another good one to use is phenolphthalein. Bromothymol blue goes from yellow to blue. I believe it's, 6.0 to 7.6. Okay, another good one to use is phenolphthalein. It's got a weird spelling. Phenolphthalein, I think, is 8.2 to 10, something like that. So it'll change color a little bit, maybe a little bit later, but because it's such a vertical, steep part of the curve, you're close enough to determining that volume accurately. All right, so that's a little bit of a longer video. Watch it again another time, or try doing some of these calculations with different volumes just to plot out why this curve makes sense. But hopefully you understood here why doing a titration is just so finicky. It's kind of hard for you to replicate because you're not able to do them in person. But in the future you'll be able to see why they're kind of sensitive this way. Hopefully you also got to see that and understand why the pH curve looks this way, and why choosing an indicator is, you can't just pick one randomly. You have to pick an indicator that is going to change color. It's going to have its endpoint as close as possible to this equivalence point. All right, that's it for this video, and this might be the last video covering content from Chem 20 because there's not much more to cover after this unless you do the bonus organic chemistry intro that I'm going to be doing in the next few days. All right, thank you for watching.